The Bohr model, which we introduced at the beginning of the chapter, showed us how electrons enter an atom in shells, right? It's got shells, like levels, okay? The quantum number gives us a little bit better of an idea as to where we can locate an electron, okay? So the quantum model tells us the probability of finding an electron in the cloud that surrounds a nucleus is proportional to the density of a cloud, right? That's your book definition of quantum model. It's not very easy to understand, but as we start working through it, I think we're going to be able to see it a little bit more clearly. This is a very rough sketch of what the quantum model of the atom looks like, right? There's many more electrons, closer to the nucleus because we fill our shells before we move outward. Okay, so closer to the nucleus, you'll find more electrons, right? Because we fill those shells before we can move on. Our big focus is going to be this something called the quantum number. Okay, and what it does is it specifies the properties of orbitals and properties of electrons. Okay, so you can think of the quantum number like the address for an electron. Okay, it's going to try to tell us where an electron is located. Okay, so the quantum number, you can think of it kind of as an address for an electron. Okay, or its coordinates, however you want to think about it. Okay, but it's going to try to give us some specification as to what shell is it in, what shaped orbital is it in, which direction is it spinning. Those types of things are going to be given to us from the quantum number. The 4 parts of our quantum number, we're going to talk about each of them individually, but in general, this is what they mean. The first tells us the main energy level. Okay, or you can think of this as like the shell level. How far away from the nucleus they are, right? That's kind of what that's telling us. Okay, if we're in the first row, we're in the first energy level. If we're in the second row, we're in the second energy level, things like that. Okay. Second part of our quantum number, or the second part of our address, tells us the shape of the orbital. So, can you tell me what types of orbitals we have in terms of shapes? Good. Circle, which is called what type of an orbital? SPD or what? Okay, so we have S orbitals, we have P orbitals, we have D, and we have F. So that's when we're talking about shapes of orbitals, those are the 4 shapes that we could have. It could be located in an S orbital, a P orbital, a D orbital, or an F orbital. Okay, and well, again, we're going to dive into each of these a little bit more specifically, but that's what we're talking about.
So the S is a circle and the P is that like...
It's like a dumbbell shaped,
What is D and F?
D and F have much more complicated shapes. I'll take you back to the diagram of D orbitals, but F orbitals are even more complicated like that. We don't need to know specifically what they look like. Yeah. Okay. So the second part tells us, first one tells us what level are we in. Second part tells us what shaped orbital is it in, right? Is it in a 1s, a 2s, a 2p, whatever. Okay, the third one tells us the orientation of the orbital. And orientation, remember, is kind of the tilt of the orbital around the axes. Okay, we saw when we were doing our demonstration the other day that p orbitals can be, like this, or they could be like this, or like this, right? This is one orientation, this is another, right? It's all about how they're tilted around the axes, or around the nucleus. Okay, so it tells us the orientation of that orbital. Okay, and sometimes you'll hear these described as like the x-axis, the y-axis, and the z-axis. Okay, it kind of works like that. So there's just 3 different ways that this p orbital can spin around the nucleus. Okay, again, we're going to look at these individually, but I'm just kind of giving you a heads up. The last one tells us the spin of the electron. So is it our positive electron or is it our negative, right? Is it our positively spinning electron or is it our negative? Okay, so the address has 4 parts to it. Those are an overview of the 4 parts. Now we're going to dive into each of those a little bit more extensively. Okay, so let's look at the first one first, this main energy level. Okay, and they go in this order. So a quantum number, for example, might look like this. 2, 0, 0, 1/2, right? That would be an example of the quantum number. It's got 4 parts, right? So that would be how it's given, okay? All right, so here we go. The first part of our quantum number is called the principal quantum number, and it's symbolized by a lowercase n. Okay, a lowercase n. And what it tells us is the main energy level of the electron. Okay, values of n, so possibilities for n are positive integers. So we can't have an energy level of 0 because there's no 0 row on the periodic table. Right? We can't have an energy level of 0 because that means they're not anywhere from the nucleus. Okay, so positive integers starting at 1 and going up to 7, 8. Okay, 8 if it's a bonded, but 7 mostly. Okay. Nope, whole numbers. Okay, so let's look at an example. If n equals 1, then that means we occupy the first energy level, right? That electron is located in the first energy level, which is the one closest to the nucleus. So for the first quantum number identifies with the block that we talk about, right? If we say it's in the 3p block, then that 3 is its main energy level. Okay, so for that first quantum number, you can think about it that way. If it's in the 3d block, then that means that the n for that quantum number would be 3. Okay, think about that. Second one is called the angular momentum quantum number, which is a lot more fancy name than it needs to be. And this is a lowercase l. And you'll usually see me write this in cursive because otherwise it looks like a 1 or something else crazy. Okay, so you'll see it usually written in cursive. So this is a lowercase l. And what this tells us, the second part again, it tells us the shape of the orbital. So I want you to look at this one next. Values of L are allowed to be 0 all the way up to n minus 1. Okay, so you go from 0 to n minus 1. Okay, L could equal any of those things. Okay. So L could equal 0 through n minus 1. The number of possible orbital shapes is equal to n. So if n equals 3, then that means L could be 3 different shapes. Okay, the orbital shape could be 3 different ones. And hopefully that this will make a little bit more sense when we look at an example, but for right now, that's what we need to understand. So you see an example down here. If n is equal to 2, the possibilities for L, they could equal 0 or 1. Right? L could be 0 or n minus 1, which if 2 minus 1 is 1. Okay, are we on the same page with that, kind of? Maybe. Okay, I really think this one will make a little bit more sense when we look at a couple examples when we look at the next slide. But those are our options for right now. Okay, if n equals 2, L could equal 0 or 1. So let's put it with them with the shapes. Okay, this is what's going to tell us what number L is. Okay, if that electron is found in an s orbital, L is equal to 0. If that electron is found in a p orbital, L is equal to 1. If that electron is found in a d orbital, L is equal to 2. And if that electron is found in an f orbital, L is equal to 3. So since we know how to do orbital diagrams already, this gives us a huge advantage when finding our quantum number, because we can just look to see what shaped orbital is it in. And then we know, okay, if it's in a p orbital, then L is equal to 1. Okay, so this table you need to have down in your notes, something that you can reference while we're doing quantum numbers. So I want to do just a quick little side step here, a quick little review, okay? And here's some examples of shapes of orbitals. Again, Madeline, you asked about the d orbitals. Okay, they can be clover shaped like this. They can be kind of circular, like cone, or like hoop shaped. They can be crazy. So there's lots of different ways that d orbital can be oriented, but we don't need to know the shapes of those. Okay, the first two. Okay, so while we're looking at this, and let's connect our n and our L values a little bit. So let's see here. If n is equal to 1, what could L possibly be equal to? Only 0, right? 0 through n minus 1. So if it's 1 minus 1, what's that equal? 0. Okay, so on our first energy level, that's what n equals 1 means. How many types of orbitals are labeled 1, right? How many 1? Do we have a 1s orbital? Yes, right? So 1s. Do we have a 1p orbital? No. So that's why 1 is not an option, right? There's no 1p orbital. So that's why for this one, L can only equal 0, because the only option for the first energy level is for it to be an s orbital. Okay, does that kind of make sense a little bit? Okay, let's say that now if n equals 2, the possible values for L could be 0 or 1, right? Now, do we have a 2? What does 0 tell us? What shape orbital? S. And 1 tells us that we could have a p orbital. Do we have a 2s and a 2p orbital? Yeah, right? We have 2s orbitals and we have 2p orbitals on our periodic table, right? That's we can do that. When we make our orbital diagrams, we have a 2p orbital and a 2s orbital. Yeah? Okay, so now let's say n equals 3. What could L equal?
0, 1, or 2.
Good. 0, 1, or 2. And what shapes of orbitals correspond with that energy level? S, P, D. So do we have 3 s orbitals? Yes. Do we have 3 p orbitals? Yes. Do we have 3 d orbitals? Yes. Okay, is this making a little bit of a connection now? Kind of. Okay, last one. N equals 4. This is as high as we'll go. If n equals 4, what could L equal?
0, 1, 2, 3.
Okay, so that means for level 4, we could have S, P, D, and F orbitals. Okay? Uh-huh.
So we won't ever go higher than 4?
We won't ever go higher than 4. Okay? As far as our L values, I mean like the shapes. We could go to energy level 5, but it would be like something that we could work with. But we're not going to look at shapes farther than that because we only have those shapes for us. Okay, but we could have an energy level of 5, but it could be a 5S or a 5P or 5, you know what I'm saying? Okay. All right, so let's move on to the third part of our quantum number. Do we feel okay about the first two right now? Kind of? Okay. Okay, I don't want to look at this. We already did this. Okay. Third part of our quantum number is an M, a lowercase m. Okay, and it tells us the orientation of our orbital around the nucleus. So when we say orientation, remember that's like kind of how it's situated around the nucleus. Is it laying flat? Is it vertical? Is it tilted? What's it doing around the nucleus, or what axes is it on? Okay. So values of M, this one is important, are whole numbers, including 0, from negative L to positive L. So we have a lot of options for M. And I'm going to show you a really easy way to find this quantum number, this part of our quantum number. Okay? Let's map out the options first, and then I'm going to show you how we narrow it down to figure out which one it is. Okay? So negative L to positive L. Let's get all these little notes down, and then we will, I don't want you to have, I don't need this part last. Okay. This is the only last part of notes I want on this page. L to positive L, and then we're going to look at something that makes sense. Okay? The very last quantum number is the easiest one. Okay, I promise. It's the easiest one. All it tells us is the spin. And the spin is either positive 1/2 or negative 1/2. That's it. Okay, if the electron in our orbital diagram is pointing up, that means it's a positive spin. If our electron in our orbital diagram is pointing down, it's a negative spin. Okay, that's it.
Is it represented by anything?
Nope, it doesn't have any letter or anything. Sometimes you'll see it with a lowercase m as well, and it might have a subscript of like ms for m spin, but usually we could just go with the last one, okay, as being the positive 1/2 or negative 1/2.
Are we gonna have to know like in order, like the first, second, third, fourth?
Yeah, it'll go in that order every time. So we'll do some practice, but you'll start kind of figuring out what order it goes in. But yeah, you will have to have them in the right order every time. Otherwise, it won't give us the right address. Okay? Okay. Are we ready to try some here? All right. Let's just look at it a little bit. Okay. I know we're still freaked out. Okay. Let's say that n is equal to 3. N is equal to 3. Let's lay out all the options for this. So all this is telling us so far is that the electron that we're looking for is in the third energy level. Does that make sense? The electron we're trying to locate is in the third energy level. So that means right now it could be in an s orbital, a p orbital, or a d orbital. Right? We have to still be more specific to look for it. But right now we're going to give all the options. Okay? So if n equals 3, L could equal what? 0, 1, or 2. Okay? So right now we're not trying to pin down its exact location. We're kind of giving some broad options as to where could it be, right? So what are the possible values for M then? -2, -1, 0, 1, and 2. Whew. Okay? These are the possible values, okay? Just hang with me for a second. M could equal -L through +L. So L is 0, 1, or 2. So we can go -2 through +2.
Oh, that makes sense.
Does that make a little bit more sense?
Yeah.
So since L can be 0, 1, or 2, it can be the positive or negative of all of those values. And 0 can't be positive or negative, so there's just a 0. Right? Okay. And then the possible values for M spin would just be +1/2 or -1/2. Okay, this is all the options for that quantum number, which we would never give all the options. Right? But I'm going to show you how we start narrowing it down now. Okay, how can we start looking at narrowing it down? How do we locate the exact electron? Okay, so let's start with one here. Let's find the quantum numbers for the last valence electron in argon. Okay, whenever we ask for the quantum number of, like, let's say if I just misspeak and I say I want the quantum number for argon, that means I want to locate its very last electron. Okay, I don't want to know where its second electron is. I want to know the very last electron for argon. So the way we can start helping with quantum numbers is to draw the orbital diagram first. So let's draw the orbital diagram first for argon. Okay, and orbital diagrams is our numbers. I'm sorry, our arrows. We're going to get to quantum numbers using this orbital diagram. I promise. It will make sense. Okay. So when I want to find the last electron for argon, which electron am I looking at? Which one am I trying to give the address for?
Very last one on the
That one, right? Would you agree with that? Does everyone's orbital diagram look like mine does? 3p, and we're argon, so we're completely full. Okay, I want to know the quantum numbers for the last valence electron in argon. So that means I'm looking for its very last electron. So I'm going to go ahead and just circle it so we know this is the one we're looking for. We're trying to give the address for this electron. Okay? So we know that it is in the 3p block. So what energy level would it be in then? N equals 3. Right. That's it. Right? We know it's in the 3p block. The energy level is 3. The shape, which is indicated by an L, what's the shape of the orbital that it's found in? It's p, right? So what number goes with the p orbital? 2. Nope, 1. Sorry, I thought I said I don't mean to throw you off anymore than that. Okay. M is equal to the orientation. So this one is where it gets a little bit tricky. Okay, but I'm going to show you a little trick we have to make it easier. It could be -1, 0, or +1, right? M could go from -L through +L, which means it could be -1, 0, or +1. So this is how we tell. We label them -1, 0, +1. So each of these orbitals, see how it has 3 lines? Those 3 lines tell us this one is in this orientation, right? This orbital is in the -1 orientation. This orbital is in the 0 orientation. This orbital is in the +1 orientation. Yeah, so that's why it lines up, okay? So this means that M is then +1. Okay, and you can just even leave it as a regular one. You don't have to necessarily put the positive. Okay, but we know it's a +1. The last thing is our spin, so I'm just going to say M sub S for spin. So now all we're doing is looking at the electron we drew. Is it the +1 or the -1? This electron that we have circled, positive or negative?
Negative.
So -1/2. That's it. You did it. The last quantum number, the only 2 options for that are +1/2 or -1/2.
So if it goes down, it's negative.
Yeah, if the electron points down, it's -1/2. If the electron points up, it's +1/2.
But if it was like +2, would it be -1? Like, I don't.
Oh, no. The only 2 options for this last number are +1/2 or -1/2. That's okay.
And then is the answer just...
This is how we would write the answer. 3, 1, 1, -1/2. You did it. You thought you weren't going to be able to do it, but you did it. Okay, so anytime I just give you the element, that means I'm looking for the last valence electron in that element, in that atom. It's a lot. It's intense. Okay? And if you are really wrapped your head around what's happening, you could even just draw the last orbital for chromium if you really wanted to. You know, chromium's in the 3D block. So if your orbital diagram, you just want to draw 3D, right, and do those, you could, because we're just looking for the last electron. That's totally up to you. Uh-huh.
Since it's like 3D4, will that one only have 4 electrons? Yeah.
Yep. It looked just like that.
What?
Okay, so let's look at our options here. Okay, what is the N? What's the energy level for this one?
3.
3. Still 3 because it's in the 3D block. So that means that L is equal to what shape goes with the D block? 2. That's okay. Look on your little chart. You had a box. Remember there should have been a table? There should be a table that goes with your L values. If L equals 0, it's the S block. If L equals 1, it's the P block. If L equals 2, it's the D. 3. Because it's in a D orbital, right? The orbital that it's in is a D shaped. Does that make sense? Yeah.
So if the 2 was there and it was 4s, n equals 0?
No, if it was a 4S, then N would be 4 and L would be 0. Okay. So this one is 3D. So remember, this one tells us the energy level. This one tells us the shape of the orbital. So since it's in a D-shaped orbital, we know that. Then L is equal to 2. Okay, SPD. 0, 1, 2. Okay, I guess I shouldn't do count it like that. Okay. The M, since L equals 2, M could equal -2, -1, 0, 1, and 2.
Oh, 1, right? Wait, why is it 3D? Like, why can't it be 3P or?
That's not where the electron ends up at.
Oh!
It's for chromium. So we're looking at chromium's last electron. So we're looking for this electron right here. Okay, so what is the value for M? 1. Okay. And what's the spin value? +1/2.
And that's just from the arrow.
Yep. So there's our quantum number. 3, 2, 1, 1/2. Whew. That's your final answer right here.
That's just so much work for
It's a lot of work. So this is what you could do. If you're feeling comfortable with orbital diagrams, you could just draw this part of it. You don't have to draw all this because you know those are all full. So if you know it's in the 3D block, just draw the 3D block and draw the electrons in there. You know what I'm saying? You don't have to draw your whole before that if you feel comfortable with it. Well, I told you that on the last one. I told you that on this one. Well, you just had to save yourself some time. Okay? You ready to try one on your own, or you want to do one more together?
I'm so ready.
All right, I'll just write it on the board, but I won't say anything. So you just do it by yourself if you want to do it by yourself. Okay, we're doing silicon, so I'll write up on the board if you're stuck, but try it on your own if you can. You can do it. You don't have to write this part.
Oh no, I didn't write them next to each other.
Yeah, your final answer should look like this. Well, don't look up there then. Okay, I want you to do sodium on your own. Sodium. I want you to do sodium on your own.